So welcome you all for the session of theory of computation. It is an introduction part. So TOC, theory of computation, is a branch of computer science and mathematics combined that deals how efficiently problems can be solved on a model of computation using an algorithm. What they are telling us, it is a branch of computer science, combined combination of computer science and mathematics to solve a certain problem. How efficiently these branch can be solved a particular problem and give you a solution. For example, if you're having a system which gets an input and it gets an output, whether it should say yes or no, which means it is accepted or rejected. So when they're talking about this, before the invention of the computers, theory of computation tells that they're having a technology which provides an abstract model of machine. It is not an original computer system, but it is an abstract model of machine which can be used to solve whether a particular problem can have a particular solution, say yes or no, or accepted or rejected. Generally, that TOC comprises three central areas. One is automata, the second one is computability theory, third one is complexity. So when we see the main area, which is known as automata theory, it deals with the definition and properties of abstract models of machine. So just now I have told you what is an abstract model of machine. These abstract models are models of computation that can be defined mathematically. It can be defined mathematically, and they are not an original computer system, but theoretically they can have even some abstract system, and they provide an input through the system and get an output, right? The simplest model of computation is finite automaton or finite state machine. So it is very, very important when you go for the finite state machine, and when we go for a further areas in this lesson, we'll know how we are dealing with this theory of computation in many areas in computer science, right? Okay. So normally the simplest model has several applications in computer science, including text processing, compilers, and interface design. The mainly the application is known as compiler construction is the main area they are using, and then they are applying the theory of computation concept, right? When we go for practically, when you know the concept, when you practically do this, you will aware of what is that thing, right? Another important model is the push down automata. The simplest model is known as finite state machine, and the next model is push down automata. So these are all the terms which is used to solve a particular problem. So the simplest problem can be solved in finite state machine, and this push down automata is much more powerful than a finite state machine, which is more powerful, and we can solve more than what we solved in finite state machine, right? When we solve the problems, when we solve the languages in this theory of computation, it will be very easy for you people. So we are going to see this and shortly, but we have to know the basic concepts, right? That's why we are seeing here, right? So this model provides a natural way of determining whether the syntax of a statement in a high level programming language is correct, and therefore it is heavily used in compiler construction. So this area of theory of computation mainly used in the compiler construction and text processing and much more. So in that scenario, finally they are invented the machine called it Turing machine, so which is found by Alan Turing. It can carry out more complex tasks than this FSM, finite state machine, and push-down automata, right? Okay. So these are the basic concept of theory of computation. So we are having three central areas, right? One is automata theory. So automata theory is a main part which you are going to be concentrated on, and you are solving more problems on that in the forthcoming sessions. And the second area is computability theory. So this computability theory tells you which problems can be solved by these sort of computers and which ones cannot. So we have already known, we have already aware of what are the problems can be solved by a computer and what cannot be solved by computers. Even computers doesn't have, even computers have some own limitation, and it can have some certain thing to solve this problem, and certain problems cannot be solved too, right? So that part will be discussed in this computability theory. And third one is you are having a complexity theory, so which tells you what makes some problems computationally hard and others easy. So we are classifying the problems according to their complexity, right? So we are segregating the problems according to their level of difficulty, and we are making problem in an effective way and solve this based on the level of difficulty. So there are three main central areas discussed in this, going to be discussed in this theory of computation. One is automata theory. It is very important one. Based on this automata theory, we are concentrated on computability theory and complexity theory. Once you go for this automata theory, you can easily well known about this concept, computability theory and complexity theory, right? So this is the introduction part of this session, right? So another thing we need to say is some of the basic terminology available in finite state machines. So it is known as finite state machine. So here we need to know the basic terminologies. For example, each and every language, for example in Tamil you are having some grammar, right? So similarly we are having the language English, we are having some grammar. So for this kind of, for our theory of computation, it has some own grammar, right? Mathematics and computer science combined grammar, right? So here we are having the basic thing is symbol. The symbol denotes A, B, C up to Z, and whatever the thing you are using. Apart from that, you are having 0, 1, 2, 3 up to etc. Right? So what are the symbols? These are all the things, characters and digits. They are called as symbols in our automata theory. And when we go for an alphabet, so the collection of symbols, they are called as alphabet, and alphabet is represented as sigma, right? For example, if you are having a collection of symbols, means here you are having A, B is a set of the strings, set of alphabets, or it's a collection of symbols, which means you are having A and B. And another variation is only you are having this alphabet D, E, F, G. So for the particular language grammar generation, only by using this A and B you are creating some grammar. Similarly, you are having these kind of only the four symbols, you can create a grammar. Other than this, you can use numbers too, right? And one more thing is string. So string here, it is a sequence of symbols, which means, for example, if I'm having an alphabet called A comma B, so it is a alphabet, right? For example, using this alphabet, I am creating a symbol. So for example, A comma B. So this is one alphabet, and you're having an alphabet, and you can create sequence of strings, or sequence of symbols using this string, right? For example, A B is a single symbol, and using this symbol we can create a string. So for example, we can create from this using A and B, we can create AA, right? BB, A comma B. So similarly, we can have for 0 1 combination, we can have so many, right? 0 1 1 0. So these are the collection we are using. Okay. Next one is language. So language, the next thing is language. The set of string is known as language. So language generally takes this sigma. So for example, if you want to define, so the language is generally the language, so it defines a language over a particular alphabet. For example, if I'm having an alphabet 0 comma 1, we can define a language, right? For example, the language can have I can denote this language L1. And for example, if I want to create a set of all strings of length 2 for this alphabet, I'm having only the alphabet 0 comma 1. So string of length means 0 0 0 1 1 0 1 1. If another case, if I'm having a language here like this, right, I can create a set of all strings of length 2 means you have A, AB, BA, B. So this is the scenario, right? Similarly, for example, L2, set of all strings of length 3. So length 3 means you are having sigma. So using sigma only, you have to create a language. So you know already, you guessed right. So it is 0 0 0 0 1 0 0 0 1 0 1 1 1 0 0 1 0 1 1 1 0 and 1 1 1. Next one is L3. L3. So this is the third example of set of all strings that begin with 0. So 0. So you are having only this denote the alphabet called sigma 0 comma 1. So 0 0 0 0 1 0 0 0 0 0 1 0 1 0 0 1 1, and you are having a 4 zeros, right? You are having no restriction, and it is going on. This set will be goes. It is called an infinite set, right? When we see this L1 and L2, we have already seen here L1 and L2. So these are finite set. So you need to know what are all the set available in this language, or a finite one or infinite one, right? So these are, we are having some restriction, and this set contains a fixed number of sets. So that is known as finite set. And this is not like that. It is not having an finite value, it is going on its values. So this is known as infinite set. And this is the introduction part of this session. Next session we will see the finite state machine, right? Thank you.